This is the second intro video on volume and area. I want to start by looking at these four regions. So, first thing I actually want to talk about is we're going to draw a rectangle within each region, kind of like the one that I had done on the worksheet that went with the last video. So, when I draw a rectangle here, we're going to call this a representative rectangle for the region. And there's a few things about it that are important. First is we're going to informally refer to that as a vertical rectangle. There's no mathematical meaning behind the word vertical or the term vertical rectangle, but I think it's pretty clear why we'd call that one vertical. So the longer part is going up and down. More specifically, the base of the rectangle is dx. In theory, what we're going to be dealing with is we're going to be talking about dividing a region like this into a bunch of rectangles like we did with Riemann sums, or like you would have done with Riemann sums in Calc 1. You would have a rectangle there, you'd have another rectangle over here, and you'd have, hundreds and hundreds of them, technically an infinite number of them, and dx would get infinitely thin. The reason we call the rectangle a representative rectangle is because you can get all of the information about the smaller rectangle on the right by looking at the bigger rectangle on the left if you just use a different x value like you would have on the previous homework. The reason for that is because the top boundary of the rectangle is the same no matter where you are in the region. So on the one on the left, the top boundary is the top parabola. That's also true of the one on the right. That would also be true of one that I drew toward the middle. The bottom boundary is the same for all three of those rectangles. The bottom boundary is on that bottom parabola on all three cases. That would be true for any rectangle within the region as long as it was between the two intersection points. So we would call that rectangle representative of the entire region. In general, we're going to have an option to use a vertical rectangle like that, or what we'll informally call a horizontal rectangle, where the base would be dy. It's not always possible, but what we would prefer is to use one that is representative of the entire region. So the blue one, the vertical rectangle, that is representative of the entire region because the boundaries don't change no matter where you draw that within the region. If I draw a horizontal rectangle within that region, one up here, the left boundary there would be different from the left boundary of one that I drew down here. The right boundary of the one on the top is different from the right boundary of the one on the bottom. It's not impossible to deal with that. It's just typically not preferable to deal with that. So what I'd like you to do, so in this first region, it's preferable to use a vertical or a dx rectangle rather than a horizontal or a dy rectangle. So what I'd like you to do is pause the video and look at the next three regions and draw in rectangles on those and determine which one is preferable, if any. So is it better to use a vertical rectangle with base dx? Is it better to use a horizontal rectangle with base dy? Does it matter? So is it possible to just use both? Or would neither one work that well, in which case we'd have to use two or more representative rectangles no matter what. So pause the video, see what you think on those next three, and then check it with me in just a couple minutes. Okay, so on the one on the second diagram, the top right, a vertical rectangle would not be ideal because if we drew one here, the top of the rectangle would be on the parabola, the bottom of the rectangle would also be on the parabola. That's still the same here, which is fine. So the top and the bottom of those would be functionally the same, but by the time we're over here, it's actually different. So the bottom boundary remained the same as the bottom of the other two, but the top boundary is the line now, not the parabola. Again, it's not like we can't do the problem that way, but usually it's harder. And so we would need to use two separate representative rectangles. We'd need one for this first part of the region and one for the second part of the region. So we would like to avoid that when possible. So then the other thing is we could use a horizontal rectangle. So if I draw a horizontal rectangle, then everything is determined based on the left and right boundaries. The base is dy. The left boundary of that rectangle is the parabola. The right boundary of that rectangle is the line. If I draw another one down here, the same thing happens. So even though those are clearly different rectangles, functionally they're the same thing, as long as you use a different y value like you would have on the previous homework. So the left boundary is still the parabola, just like it is on the top rectangle. The right boundary, I don't have it quite going over there, but the right boundary is the line, just like it is on the top rectangle. So in the second diagram, we would prefer a horizontal rectangle with base dy. On the third one, you can use a vertical rectangle. So the top of the vertical rectangle would be that curved function, probably a square root function of some sort, with base dx. No matter where I drew that within the region, it would be the same. Also, I could use a horizontal rectangle. No matter where I draw that within the region, the left boundary would be on the square root function or whatever that curved function is. The right boundary would be on the line. The base would then be dy. In the fourth region, a horizontal rectangle would change depending on whether it's toward the top part of that region or the bottom part of that region, but a vertical rectangle would not. So if I draw it here, the top is on the top curve, the bottom is on the bottom curve. Even though this rectangle over here is much smaller, the top and bottom boundaries are the same as the top and bottom boundaries on the one on the left. So we would prefer a vertical rectangle which has base dx. Okay, the important part of that is that when you do most area volume problems, typically the easiest way to look at it is to draw a graph first and then determine which rectangle you're going to use before doing the volume and area problems. So you want to get a good picture and then you want to draw the rectangle. That will dictate which variable you're going to use. So if you're using a vertical rectangle with dx, then everything you write in the problem should be involving the variable x and not the variable y. So if you're using the letter x, that's fine. If you need to describe y, you will need to do that in terms of the variable x. The opposite's true if you're using a horizontal rectangle with dy. When you're using dy, you can use the variable y, but you cannot use the variable x. If you want to describe x, you would need to describe it in terms of y. Okay, let's look at this region. So it says, consider the region bounded by y equals x squared plus 5 and y equals x plus 11. All right, when we're talking about volume and area problems, which we're moving into, you should first look at the region that you're dealing with. So you should get a good picture of the region first. So let's draw that. When we draw y equals x squared plus 5, that's a parabola shifted up 5. And then when we draw y equals x plus 11, that's a line with slope 1 and y-intercept 11. So it looks something like that. We want to really focus on the overlap of the region. So we want to extend this so that it connects there. And we actually don't need this top part. And so I'm going to erase that and just redraw a shorter part of it. And so we get something like that. The graph doesn't need to be perfect and it doesn't need to be to scale, but it needs to be where you can really look at the overlapping part of the region, the region that's contained by the curves. If you start drawing a picture like this, so when you draw like y equals x squared plus 5, if you're drawing that, and then y equals x plus 11, and you're drawing that, there's nothing wrong technically with that picture. It's just harder to look at that picture and determine what's going on. And so if you do start with the picture on the right, kind of take time to redraw the picture so you're kind of zooming in on the overlapping region. When you're doing area volume problems, you're going to be looking at that diagram a lot, and it's important to know where everything is relative to each other. It's also important to determine the intersection points. So when you're doing the region, so based on the region, we should kind of be doing several things. First, get a good sketch. Second, we should find any boundary points. So find intersections and boundaries. And so here we need to find the intersection points. Because they're both solved for y, we can set them equal to each other. Okay, so we're going to do, to find the intersection points, we're going to say x squared plus 5 equals x plus 11. We're going to solve that for x, so we're going to get 0 on one side. We're going to factor that and get x minus 3, x plus 2 equals 0. That gets us x equals 3 and x equals negative 2. The point on the right is pretty clearly where x is 3. You can plug the 3 into either equation to get that y is then 14. And it's smart to plug it into both. So like 3 squared plus 5 is 14. 3 plus 11 is 14. That's more indication that we're correct about that. And then this point is where x is negative 2. And you can plug that into either function and get positive 9. Okay, so we find the intersection points. Another boundary that's important is that this y-intercept is at 5. And so you want everything kind of on the outer edges of that region. So the top is 3 comma 14. The right is also 3 comma 14. The left is negative 2 comma 9. And the bottom is 5. So the top is negative, or is 314. The bottom is 0, 5. The left is negative 2, 9. And the right is 3 comma 14. Okay, so you want to get a good sketch. You want to find the intersection and the boundary points. And then you want to draw a representative rectangle. So when you do that, you want to look at which is preferable: a vertical rectangle with base dx or a horizontal rectangle with base dy. And so on this region, a vertical rectangle is preferable because the top boundary, no matter where you draw it within the region, is on the line y equals x plus 11. The bottom boundary, no matter where you draw it within the region, is on the parabola y equals x squared plus 5. If you drew a horizontal rectangle with base dy, the left boundary would change. So for most of the region from negative 2, 9 and up, the left boundary would be on the line. From negative 2, 9 down to 0, 5, the left boundary would be on the parabola. That would mean that every problem we do, we would need to set up with 2 separate setups. That's completely fine to do. It's just harder. So if we can avoid that, we do. All right, so based on the region alone, we should be doing these things. We should be getting a good sketch of the region. We should find the intersection and the boundaries, and we should draw a representative rectangle. That's really without regard to what the question's asking. So all that I've written on the screen so far to do is to consider the region. Well, if you think about that, that really just means think about the region. I'm not actually asking you to do anything, but that's understood that when we do look at the region, we should be doing these things. We should be drawing, well, I just erased them, but we should be drawing it. We should be finding the intersection and boundary points, and then we should be drawing a representative rectangle. Okay, so I want to look at several problems where the directions sound like this. So I want us to find a formula. Find formulas for the distance from the given line to each of these two things. So part A, we'll do those in blue. Or no, let's do them in a different color. Let's do those in purple. So for part A, to the farther end of the rectangle. For part B, we're going to do the closer end of the rectangle. Okay, so we're going to do a few problems. So like number 1 is going to be y equals 20. And so what I'm asking is I'm saying, okay, let's find a formula for the distance from the given line. The given line is y equals 20. So from y equals 20 to the farther end of the rectangle and from y equals 20 to the closer end of the rectangle. Okay, so let's look at y equals 20. So y equals 20, and we'll do that in green. Y equals 20 is a horizontal line, and it's somewhere above the region. And just because I've got instructions written up there, we're going to put it there. Not to scale, but it's above that. So it's 6 units up, so a good bit higher, I guess. But we're looking at the distance from that line to the farther end of the rectangle and the closer end of the rectangle. You were doing similar problems like this on the previous worksheet, and what it was doing is it was giving you various values of x, and you were finding the distance from like the line to point A and line to point B, or line to the top of the rectangle or line to the bottom of the rectangle, and getting those numerically. And then it was asking to do that for any x in the region and get a formula. I'm going to erase this, consider the region bounded by. Okay, so you were doing that for a bunch of different numeric values, and then you were doing that in order to find a formula for any x. And so now we're asking just for the formula. So for part A, we're looking at the distance from the given line, so y equals 20. So from here to the farther end of the rectangle. We'll look at the blue rectangle. Which end of that rectangle is farther away from y equals 20? The bottom of the rectangle is farther away from y equals 20. The distance between that line and right here, the distance between the line up here and the farther away end of the rectangle, the bottom of the rectangle, that is a vertical distance. So in order to find that, you take the top y minus the bottom y. Well, the top y up here is 20. The bottom y is whatever the y value is at the given x value. So because it's dx, we put everything in terms of x. The y value there, it's on the parabola, so it's x squared plus 5. So top y is 20, bottom y is x squared plus 5. That simplifies to negative x squared minus 5, which is the answer to part A. For part B, we're looking at the distance from the line, from the line to the closer end of the rectangle. So y equals 20 is up here. Looking for the distance from the line to the closer end of the rectangle. So if we look at that again, the line is here. The closer end of the rectangle is here. We're going to take the top y minus the bottom y. The top y is 20. The bottom y is x plus 11. That simplifies to negative x plus 9, and that's the answer on this part. Okay, so I'm going to put a second problem up. I'd like you to try this. So if we have y equals 3, pause the video, see if you can set up formulas for the distance from y equals 3 to the farther end of the rectangle, and for the distance from y equals 3 to the closer end of the rectangle. Okay, so y equals 3 is a horizontal line, and because that y-intercept is at 5, the horizontal line's under the region. So this is y equals 3. All right, so when we look at the farther end of the rectangle, now the farther end of the rectangle is the top of the region, or the top of the rectangle. The line, the horizontal line, is y equals 3. So we're looking for the distance between those two purple arrows. That is a vertical distance. So the distance from the top y to the bottom y. We take the top y minus the bottom y. The top y is x plus 11 because it's on that line. The bottom y is 3 because it's on the horizontal line. That simplifies to x plus 8. When we look at the next one, we're looking at the distance again from the line y equals 3 to the closer end of the rectangle. So y equals 3 is here, and we want the closer end of the rectangle. So closer to this line is the bottom of the rectangle in this case. So if you go back and look at the first one, it was the top was closer. Here the bottom is closer. So you do need to visualize that. For part B though, now this is a vertical distance. The top y is x squared plus 5. The bottom y is 3. And that simplifies to x squared plus 2. So it's important why the subtraction is reversed. Also, it's important why x plus 11 is the farther end of the rectangle on problem 2, and x squared plus 5, the parabola, is the farther end of the rectangle on number 1. Okay, I'm going to put 2 more lines up, and I'd like you to pause the video and try these. So the same questions, if I'm using y equals negative 7 and if I'm using the x-axis. Okay, so find formulas for the distance from the line that I'm giving you, y equals -7, to the farther end and closer end of the rectangle, and then from the x-axis to the farther and closer end of the rectangle. So pause the video, try those, and then check them with me in just a minute. So y equals -7 is down here. The first problem, we're looking at the distance from the farther end of the rectangle to y equals 7. The farther end of the rectangle is the top of the rectangle, which is actually y equals x plus 11. So the y value there is x plus 11. The bottom y is -7. That simplifies to x plus 18. For part B, the closer end of the rectangle is the bottom of the rectangle. So we take the top y within that. The top y within that is x squared plus 5. The bottom y is -7, and that simplifies to x squared plus 12. When we're looking at the x-axis, it's basically the same thing, but it's a little bit weird. People tend to want to write something here that you shouldn't. And so let's start with the farther end of the rectangle. If we're looking at the x-axis, which is here, the farther end of the rectangle happens to be the top. So we take the top y minus the bottom y. Well, the y value at the top of that rectangle, again, is x plus 11. So we take x plus 11, and then we subtract the y value at the x-axis. And so the y value on the x-axis is 0, and we get x plus 11 minus 0, which is x plus 11. You just want to be careful there. A lot of people want to do minus x when it's the x-axis, or sometimes minus y. That's not what we want to do. We want to subtract the y value at the x-axis. The y value on the x-axis is 0, so we subtract 0 there. So when we look at part B, we're looking at the distance from the closer end of the rectangle to the x-axis. That's a vertical distance. So you take the top y is x squared plus 5, minus the bottom y, that's again 0, so we get x squared plus 5. It's important to notice what you're subtracting, what order you're subtracting everything in, and why you're subtracting them in that order. So even when you're subtracting 0, every distance we should be thinking as the difference of two different things. If it's a vertical distance, it's always top y minus bottom y. If it's a horizontal distance, it's always right x minus left x. And so always start with subtraction, and then if it simplifies to something else, that's completely fine. Okay, so I want to look at another set of problems. So first 4 were horizontal lines. Any horizontal line above the region would have worked like problem 1. Any horizontal line underneath the region would look like the second 3 problems, 2, 3, and 4. So what I want to look at now is if we have vertical lines where they're to the left and to the right of the region. And so now let's fix that, and then let's look at number 5, I believe, and we'll say x equals 8. So x equals 8 is a vertical line to the right of the region. X equals 8 over here. And we're going to look at now the distance between x equals 8 and the farther and closer end of the rectangle. Pause the video and think closely about what that's asking, and think what's weird about that. Okay, so when we're talking about this, there is no farther and closer end of the rectangle because in theory the rectangle's infinitely thin. So the distance from here to here and the distance from here to here is the same whether you're on the top or the bottom. And if it was left and right was different, it would actually be different, but it's infinitely thin. And so when we're looking at this, we really are going to have the same answers for both of them. So it's A and B would be the same, or we can just change the directions from the given line to the rectangle. Okay, so let's do that. Okay, and so when we look at this, the distance from x equals 8 to the rectangle is the distance from there to there. That is a horizontal distance. So when we do horizontal distances, we take the x on the right minus the x on the left. Pause the video and write what you think you would get for that. So the distance from the given line to the rectangle. Right x minus left x. Pause it, come up with what you think, and then check it with me in a second. Okay, so we take the right x minus the left x. The right x is clearly 8. The left x, it's important that it is x, and it is not x squared plus 5, and it is not x plus 11. X squared plus 5 is the y value on that parabola. X plus 11 is the y value on that line. We don't want the y value, we want the x value. If you think back to the worksheet on the previous video, you would have taken the 8 there minus whatever the x I gave you was. So if I told you that this was x equals 1, the distance between those is 7. It's 8 minus 1. You don't plug the 1 into either of those equations to get it. And so you just subtract whatever you're given. So here it's x minus 8. That's a much easier formula than what we were getting on the others, but it's much easier to mess up because it seems like it should be harder than that. The answer to that one is x minus 8. So then let's put up a couple more and let you try them. So if I have x equals 12, and if I have x equals negative 6. So pause the video, try those, see if you can come up with a formula from the line x equals 12 to the rectangle, and from the line x equals negative 6 to the rectangle. Okay, so x equals 12, we'll do that one in red. X equals 12 is a vertical line again to the right of the region. We're looking then at a horizontal distance, so we take the right x minus the left x. The right x is 12, the left x is x. If I look at x equals negative 6, that's to the left of the region. So we're over here. Again, that's a horizontal distance, so we take the right x minus the left x. The x on the right is x. The x on the left is negative 6. So we get x minus negative 6, which simplifies to x plus 6. Okay, let's look at two more things related to this same region. I've just redrawn it so it's a little bit cleaner picture. So the 8th problem I want to talk about is let's find a formula for the height of the rectangle. So this is without regard to a line outside of the region. It's just looking at the height of the rectangle. A quick comment about the term height. So most of us think of height as being up and down because we talk about height of a person. And for a rectangle with base dx, height is up and down. When you're doing similar problems to this, we're going to want to think of it, if we're using a dy rectangle, where the base is dy and the height is sideways. When we're using a vertical rectangle, we're going to think, okay, the base is dx and the height is vertical like we would normally think. And so just real quick, it's important to note that because normally we think of height as being up and down, and height really is just, in this context, it's just whichever direction is perpendicular to the base of the rectangle. Okay, so with that in mind, I guess it doesn't really affect this problem much, but it will affect stuff we do in the future a lot. So with that in mind, pause the video, see if you can come up with a formula for the height of the rectangle in the diagram, and then check it with me in just a minute. Okay, so the height of the rectangle, we'll call this actually h of x. We take the top y minus the bottom y because in this case, this is a vertical distance. So the top y is the y value on the line x plus 11. And the bottom y is the y value on the parabola, which is x squared plus 5. That then simplifies to negative x squared plus x plus 6, if you distribute the negative. But that is the height function. Again, we should be thinking of distances starting as subtraction. So in this case, the top y minus the bottom y. Okay, one more problem I want to talk about, but the whole point of doing this for one rectangle is that a Riemann sum lets you calculate things with reference to that single rectangle, and then the Riemann sum adds them up for all of the rectangles that you want to deal with. The integral is the limit as the number of the rectangles approaches infinity, which means that the width or the base of the rectangle dx, or in some cases dy, the width approaches 0. So the number of rectangles approaches infinity, the base dx approaches 0. That gives you the definite integral, which we can think of as taking all of the rectangles in the region and adding them up. So what I want to do is I want to calculate the area of the region. So we're just going to set up the integral, but we're going to set up an integral used to find the area of the region. Not of the rectangle, just the rectangle, but the area of the entire region. The way we're going to do that is we're going to use the area of the rectangle, and then the integral is going to add up the area of every rectangle within that region. So in general, we can think about area as being the integral of the area of the rectangle. Well, the area of the rectangle is going to be base times height. So it's the height of the rectangle times the base of the rectangle, which is dx. In some problems, the base of the rectangle would be dy. Textbooks would take you through a formal proof of this integral. It would show the Riemann sum, and it would be worth reading through that. An easy way to think about finding the area of the region is we need to find a height function, and then the integral will be the height times the base, and it will add up the area of all of the rectangles, getting the area of the region exactly. So in this problem, what we want to do is we want to find the height function, and the height function is the height of the rectangle. If we hadn't done problem 8, we would do this the same way. So we take the top y minus the bottom y. That's x plus 11 minus x squared plus 5. That's negative x squared plus x plus 6. The base is dx. So the area of the region is the integral of the height function, negative x squared plus x plus 6, times the base dx. And now we want to add up all of the rectangles in the region. This is dx, so we want from the smallest x to the largest x in the region. The smallest x in the region is negative 2. The largest x in the region is positive 3. This integral would calculate the area exactly. This would be an easy integral to calculate. You just use the power rule on each of those 3 parts. You plug in the 3, plug in the negative 2, and subtract. Okay, so that's how we find area between 2 curves. We use this height function times either dx or dy. The first 7 problems, we're finding different functions that are relevant in volume problems, and we will look at that in the next video. Thanks for watching this one.